Okay, so now what we're going to do is we're going to look at the density operator, right? The density operator is going to be our new, like say, fundamental thing that we're going to be considering. We worked out a lot of stuff about the density operator already, so I'm not going to redo that for sure. Right? We worked out the Liouville equation, which was the equation of motion of the density operator. We have thought about various measures of the density operator, like the trace of rho squared, and so on. We have definitions about pure and mixed states, right? So those are the things that we should be able to remember pretty well. And hopefully, if you don't remember those, go back and check them out in the earlier lecture segments, okay? Or read about it in Wikipedia. I mean, certainly didn't discover all this stuff, so there's other places that you can find out. All right, now one thing I do want to do is remind or look into a property of the density operator that's kind of interesting, which is how it depends on time. Okay, how various trace of the density operator depends on time. So for example, we know that the trace of rho, and just remember what that means. It means the sum of the diagonal elements if you think of it as a matrix. The trace of rho, which you could write, for example, in this way: sum on alpha, alpha, rho, alpha, which is the same thing as just writing sum on alpha, rho, alpha, alpha. We know that this is equal to 1. Okay? And we're going to now consider what happens as a function of time. So one thing that we learned about the density operator is that we can write it down as a function of time. And if provided that it obeys the Schrodinger equation, or the Liouville equation, whatever, then there's a time evolution operator, which brings the initial density, rho of t naught, to the value it will be at t. And it's this kind of transformation using the full time evolution operator, not one of these little pieces of it. Now, of course, thinking ahead, we are, of course, going to use these perturbative expansion versions when we want to consider how time-dependent perturbation theory works when our central object is the density operator. Now, one thing that we might want to think about a little bit is how do these things evolve as a function of time? Okay, and so let's look at trace rho. So you might say, how do I know that the trace of rho as a function of time is always going to be equal to 1? How do I know that? All right, so what you do is you write down trace. Now, I'm going to write down the u's just as u's, and trace and rho, the initial rho, I'm going to write it down as rho naught. All right, so we're going to do this as trace u, rho naught, u dagger. Okay, and then I'm going to use a most remarkable property of a trace, which is the so-called cyclic permutation invariance, which is to say that if I have a trace of 3 matrices, whoops, I guess I could have written it that way if I wanted to, but trace ABC, it turns out the trace of ABC is also equal to the trace of CAB, and it's also equal to the trace of BCA. Now, how do I know that? It's because if I write them in a triangle like this, as long as I keep the order on the triangle, then I can permute them however I like, and the trace will be equal no matter what I do. So ABC will equal BCA, that's this one, as well as CAB. And then if you have more than 3 operators, well, then you can just break it into chunks, and it can still work this way. Okay, so what this means then is I can, instead of A, B, and C, I have U, rho naught, and U dagger. So I can move them around. So this is equal to trace U dagger, U, rho naught. Well, we know what U dagger U is, because U is a unitary operator. The dagger is equal to the inverse, so this is equal to 1. So this is equal to the trace of rho naught. So whatever the initial value of the trace was, if it evolves according to unitary evolution, which for us means according to the Schrodinger equation or Liouville equation, then the whatever the initial trace was, it will stay that way. Now you can do this for rho squared, plug in rho squared, same deal, it's going to be the same thing. All right, so this proves that if you have unitary evolution, trace of rho squared will equal of t will equal trace of rho squared for t naught. Now remember what rho squared told us. When trace of rho squared is less than 1, we call this the mixture. All right, so what that tells us is something very important. If your system starts out, let's say, in a pure state, when trace of rho squared equals 1, there's no way by unitary evolution that you can ever achieve a density operator that has a mixture. Vice versa, if I start out in a statistical mixture, like let's say a Boltzmann distribution of states, there's no unitary evolution that can put me into a pure state. Okay, that is pretty remarkable. How are we going to get this? I mean, the basic idea that we're going to have in our mind is that we take a quantum system, maybe let's say it's in the ground state, so that you could call that a pure state if you want. Then we're going to excite that with a laser, make a coherent superposition of two states that might emit field, or we might add another field interaction, two field interactions, which will cause an excited state population, as we showed in our discussion section. All right, and then the system would stay in an excited state. Ultimately, we want this thing to relax, right? We want to go down to another, if I have it in a perfect, this beautiful coherent superposition of states, I expect that coherent to get screwed up by the environment. I expect a dephasing to occur. Well, that's not possible with unitary evolution. And unless you include the entire wave function of the entire universe, or every atom in your solvent molecule. Well, we're going to find out ways to deal with this. All right, so this is the sort of the conundrum. Where does the dirt that we know is in nature come from? Because it sure does not come from unitary evolution. If you started out in a pure state, you'll stay pure. If you start out in a mixed state, you'll stay mixed, at least by the same amount. All right, so what we're going to do next is work more on the density operator. Okay, and so we've already derived the Liouville equation, which I'll rewrite. Trace of, I'm just reading that. The time derivative of rho is equal to minus I over h bar times this commutator, h of t, rho of t. All right, that's the Liouville equation, or the Liouville-von Neumann equation, whatever you want to call it. Now, one thing that we need to do is we need to consider what happens when you calculate something like trace rho times some other operator. Now, if you already know the answer, then you know what this is equal to, but let's see what it is anyway. All right, let's consider that we have a pure state, just for simplicity for this derivation. Then we know that this is equal to trace psi A. Okay, and what we're going to do now is we're going to write down explicitly what trace means. I wrote it up here. This is going to be the sum on some basis, obviously, that you need to choose. Okay, and now what you see is we have two numbers, right? This scalar product is a number. This scalar product is a number. So we are free to move these however we want. So if we move this over here, we will have the sum on n, psi A, n, 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 psi. So just as inserting 1 can be very useful in derivation, so can removing a 1 be very useful. What do I mean by that? Well, we've inserted essentially 1 here, right? This is the spectral resolution of the identity. Whatever the basis is that n is the vectors of, then this is equal to 1. Presumably, of course, we put in a complete basis. So this comes out. So this is equal to psi A psi, which tells us then that this is equal to the expectation value of A. Okay, so trace rho A is equal to the expectation value of the operator A. This teaches us how to do expectation values when our main object is the density operator. Now, what about the order here? Well, I told you something about how you can move things around in a trace, but I only see 2 here. So what do I do about that? Remember how multiplying by 1 can be very useful? Let's do multiplying by 1 now. We'll do multiplying by 1 by putting in the identity operator, I. Now we have a triangle. So we can write rho A I back to rho, which means that this is equal to trace. So rho AI is what I have now, but it's also equal to I rho A. And do we really need to write I's all the time? No, we don't. So this is also equal to trace rho A. So what you notice is that computing the trace doesn't depend on the order that you have rho and A. Well, that can be convenient for your formulas and also for your derivations of things. Okay, so for example, one of the things that we're going to want to be able to do in the class is compute psi of t, of course, or rho of t, and then use it to compute an expectation value of an operator relevant to spectroscopy. Well, what's the most important operator in spectroscopy? The dipole moment. So we now know that mu of t is nothing other than trace rho of t mu of t, or mu t rho of t. It doesn't matter. All right, and that's the interesting thing about traces and using them to calculate expectation values. So something that we might want to do is compute, mu of t I put in terms of it could be, this mu here could be truly time dependent, meaning it might be a field, or this might be mu times E or something like that. Or I might think of a mu as a sort of a constant operator, and then I just allow rho to evolve according to the time evolution operator. Of course, we'll do that, and then we will do it in such a way that we evolve it perturbatively. You can imagine, for example, that there's an external influence. So now we have a coupling of the molecule to the environment, which I could mimic by putting in another molecule or another two-level system, and I would have a coupling between them. This could be like the system, and this could be like a bath or an environment. And maybe I'll have the coupling either fluctuating, or I might have the bath frequency fluctuating stochastically, randomly. So I might think of some coupling with the environment changing like this, maybe because the molecule is moving around, or I can imagine that the environment is moving around. So now I have something that depends as a function of time. This is all going to be encoded one way or other in mu of t. Right? And you'll see how we can derive expressions for line shapes by knowing about how the fluctuations occur. Okay, so we're not going to get there yet, but this is one of our big goals. One other property of the trace that's very interesting is the idea that the trace itself does not depend on the basis that you use. And that is a really amazing thing. But it just follows from this. So imagine I have, for example, an operator A. I can transform this operator into another basis. In some sense, when we say something is diagonalizing, then that's what we're doing. And so we can transform it to another operator, which I'll call A primed, which is equal to B, A, B inverse, where the matrix or the operator B is this transformation matrix that allows me to transfer from one to the other. What's an example of this? This could be the Hamiltonian written in some other basis that's not its own eigenvectors. And then when you find those eigenvectors by diagonalizing it in quotes, you're finding the matrix of eigenvectors is B. And then if you do B, Hamiltonian B inverse, you'll get back a Hamiltonian that is diagonal. And that goes for any operators. I just picked the Hamiltonian because it's familiar to people. So if I imagine then that the trace of whatever A happens to be can be, we want to ask the question, how is this related to the transformed version of A? Well, we write it down. Trace B, A, B inverse. What do we see? B can come over because of the cyclic permutation invariance, and so we can then write trace B inverse B, A, which of course is equal to trace of A. So this tells us that whatever you get here, you can transform it into whatever other basis you want, but the trace will be identical no matter what basis you choose. Right? So that tells you when you use the density operator to calculate expectation values, it doesn't matter what basis you use. That's a really beautiful and interesting thing that sometimes can be quite useful in derivations. All right. Now we really have worked out already quite a number of things about the density operator, right? So we don't need to go into too much detail. What I'm going to do is I'm going to show you something kind of interesting, right? We're going to look at the matrix elements, or the elements of the Liouville equation. So if you think back to something that I showed you early on, we wrote the Schrödinger equation, and then we wrote the Schrödinger equation in a basis. And then from that, we recognized that that generated for us a system of linear differential equations. All right, and that then could be plugged in the case of our two-level system, to any old differential equation solver, and you can solve the Schrödinger equation to your heart's content. There's nothing unsolvable about it. What's hard? What happens if the basis starts to get large? Then, of course, the matrix gets bigger and bigger and bigger, and that's why we don't just go around solving the time-dependent Schrödinger equation for gigantic things. All right, so what we're going to do next is we're going to look at doing the same thing, but for the Liouville equation. All right, so let's see how that works.